So in the previous class, we looked at a language for which we built both an NFA and a DFA, and we also saw the difference between the simplicity of NFA and the complexity of DFA, right? So NFA looked so simple. It had just 4 states, few transitions, and easy to draw, easy to construct, easy to understand. Whereas DFA has multiple states, more states, and also more transitions. It is more complicated to construct, right? So NFA and DFA are equally powerful, but NFA is more convenient. So that's the whole point. All right, so let's look at one more example of NFA today. Yeah, build an NFA, say N3, which recognizes the language L, which accepts strings of the form a power k, where k is a multiple of 2 or 3 over the alphabet A with a single element A. Okay, so to put it simply, it has strings which are constituted of only A's, like A, AAA, and so on, out of which some strings lengths are multiples of 2, some strings lengths are multiples of 3. Only those kind of strings should be accepted, other strings should be rejected. Okay, so this will not accept a string with a single A. This will accept a string with 2 A's. This will accept a string with 3 A's. This will accept a string with 4 A's because 4 is a multiple of 2. This will not accept a string with 5 A's. And so on. So multiples of 2, multiples of 3, they will be accepted. Even empty string will be accepted because that is multiple of 2 and 3. 0 is a multiple of 2 and 3. All right. So build an NFA which accepts only these strings. Is everyone done? Done? Okay. Anyone else? Yeah, you tell me. How many states are there? 4. Yeah, can we have some silence, please? I hope you know the meaning of silence.
On receiving an A, Q1 goes to Q2 and Q3.
Okay.
Q2 receives an A, goes back to Q1. Q3 receives an A, goes to Q4. Q4 receives an A, goes back to Q1.
That's it. Is this correct? Correct or no? Correct.
I've taken a 5.
Yes. It's not correct because it will also take 5 length string. 5 ways it will accept. Yeah. Okay. So let me just say this. No. Okay. Anyone else? Okay, so let me give you a clue. So there are 2 ways of solving it. One is trying to build one complex machine which handles both multiples of 2 and 3 at the same time. In the sense, it's like an LCM problem kind of a thing. That's what you're trying to solve. But what if this problem is modified to include many other cases, like multiples of 2, multiples of 3, multiples of 5, 10, 20, so many such cases? Then will you again try to think of the intersections of all these numbers and try to build one single machine for all, the complex case? That is too complicated, right? Another way is this one single complex problem or multiple simple problems? It's multiple simple problems because it's a multi-part problem. What is a multi-part problem? It has subparts. So what are the subparts here? It's either a multiple of 2 or it's a multiple of 3, right? So how do you solve a problem with subparts? Why do we break a problem into subparts? Yeah? Separate machines. Yeah, so basically we solve each subpart individually and then combine them, right? So now think along those lines. Try to build a machine for only multiples of 2 and try to build a machine for only multiples of 3. Now try to combine both these machines. This method can be extended to any number of scenarios, like multiple of 2, multiples of 3, multiples of 5, multiples of 10. You can have 20 such numbers, and for each of these you build separate machines and then combine all of them, right? So there is no upper limit on how many cases you can handle. Yeah.
It's kind of like the union of regular lines.
Yes.
That would result in a DFA? Is there a way to get an NFA?
We didn't discuss the algorithm for NFA, but given our understanding of NFA, you can do it easily. You can do union of two NFAs. First, someone tell me what is the machine which accepts strings of lengths which are multiples of 2? Anyone? Yeah. Two states. First state is an accept state. On another day, it comes back to the first state. All right. So this is for multiples of 2. What about multiples of 3? Machine which accepts strings of lengths which are multiples of 3. Yeah, 3 states. Let me have other numbers. Q3, Q4, Q5. Then Q3 is the start state. Sorry, you said start state. Is also final state? Okay. Then Q3 to Q4 on A, Q4 to Q5 on A, then Q5 to Q3 on A. Okay, this will accept strings of lengths which are multiples of 3. So now you got two machines. Now you need to combine them. How will you combine them? Yeah, loudly. Another state. Okay, so let me say Q0. Now how do I combine? Q1. Yeah, Q1 and Q3. But they can't be empty, right? I need some label on these transitions. Yeah, it's just epsilon transition. That's it. So basically, if you remember, I told you, whenever a particular state has two or more outgoing arrows for the same label, you can think of it as an OR condition, either this or that. So that's exactly how we understood parallelism also. Like in one of the previous examples where Q1 on input 1 goes to Q1 and Q2. So basically it is taking both the branches. So either this branch may work out or this branch may work out. It is trying both the things. All right. Now, same thing. Now it's the reverse. We know what are the two branches, what are the two outputs we need. Here there are two machines, either multiples of 2 or multiples of 3. We know it is an OR condition. Now all that we need to do is to translate it into two outgoing arrows. Earlier, I told you whenever there are two outgoing arrows, it is like an OR condition. Now we know what is the OR condition. Now we just need to add or convert it to two outgoing arrows. And another thing, I don't want to add any more information with these outgoing arrows. I just want the OR condition, nothing more. I just want to outgoing errors, nothing more. So I will use epsilon transitions. So the moment you enter the start state, the moment you like switch on the machine, it will just sort of fork itself into two machines and run both the machines parallel. So if one of the machines accepts the string, this overall machine accepts the string. Yeah. Okay, tell me. Okay. Okay. Hmm. Hmm. Yeah, that's what he said. Hmm. Back to Q1 on A. It will accept 5 A's. Then A, again A. Yeah.
What if we have a separate accept state, Q4, then Q3 goes back to Q4, Q4 on A goes to Q.
In this machine,
In this case,
the one he said just now. So you are saying I have an accept state Q4. Q3 goes to Q4 on A.
yes.
Okay.
And Q4 goes to Q2 on.
Q2.
Actually, that wouldn't work.
Yeah. None of these combinations will work. You need to have some epsilon transitions. Either the way I have epsilon transitions with a new start state, or within the machine, the way you're trying to build machines, within those machines, there should be epsilon transitions. Okay. So without epsilon transition, this is not possible. Yeah.
Is there a way to check that whether we need an epsilon transition to do this?
No, there is no automatic mechanical algorithm to check whether we need an epsilon transition or not, or whether we need a particular transition or not, or whether a particular machine is the machine or not. There is no automatic way. It's mostly trial and error method. That's why it is a bit of intuition, creativity, all that. So there is no algorithm to design an algorithm. It is something like that. You're basically designing an algorithm. It's like if I ask you to write a program for this, that program is an algorithm. So you don't have a meta program to write any program for a given problem like that. Yeah. Yeah. There can be more answers. Yeah. Okay, so you are naming them like that. All right, let's do it quickly. Let's not spend too much time on that. Q naught, QA, QAA, and Q triple A. All right. Okay. Then, okay. And this on A. All right. This will also accept 5 A's, no? 1, 2, 3 comes back. 1, 2 comes back. This is the final state, right? A is final state. A is also final state. Okay. Yeah, but still, it will accept 5 A's also. Okay. Yeah. All right. So this is nothing but union of two NFAs, union of two languages. We'll actually see the proof later, but this is much easier than combining two DFAs to build a union DFA. NFA's union is so easy, right? Okay. Okay, so far we have seen only examples of NFAs. We haven't seen the formal definition of NFA so far. So let's look at that. A non-deterministic finite automaton is a 5-tuple same 5 elements q, sigma, delta, q naught and f, where q is a finite set of states, sigma is a finite alphabet, delta. So can someone tell me what is the domain and range of delta for an NFA? Yeah? Sorry? Epsilon. Yeah.
The domain should be state and an alphabet.
That is not domain.
Like domain should be the set of alphabets cross the set of states. Q cross sigma.
Right. So q cross sigma union epsilon. So that we write like this. So basically sigma subscript epsilon means sigma union epsilon. Okay. What is the range?
Power set of states.
Power set of the set of states. Is it right? Or any other answers? See, always think in terms of, first try to think in terms of elements, and then try to now map these elements to their respective sets. So take an example of DFA. In DFA, what, say you have some state Q1, you have some alphabet, some symbol A, maybe you go to Q2. Okay, this is the function. Now map each of these elements to their corresponding sets. This comes from set Q, this comes from set sigma, so their cross product. This comes from set Q. Okay, so now what will be the domain of this delta? Q cross sigma to Q. Okay, but in NFA, what is the difference? Say delta of Q1 comma A may be a set, maybe Q1 comma Q2. All right, now again, this comes from Q, this comes from sigma. Now this entire thing you should take as an element. All right, you should not say, okay, where does Q1 come from, where does Q2 come from? This entire thing is one element. Output is always one for a function. Output is not many. Okay, now this entire element belongs to which set? Belongs to power set of Q, because in an NFA, a given state and an input symbol map to a set of states. This set of states is nothing but a subset of Q. Okay, so what is that set which has all the subsets of Q as its elements? That is the power set of Q. Okay, so the range is power set of Q. All right, Okay. Let's leave it like this. Then next one, Q naught belonging to Q is the start state. All the subsets of Q and this one, sigma subscript epsilon is nothing but sigma union epsilon. Okay. We may need some space. All right. So that's the formal definition of a finite, non-deterministic finite automaton. Okay. So let's take an example and quickly give its formal description. So let's take the first example, N1. All right. The formal description of N1 is the 5 tuple Q sigma delta Q naught and F, where what is Q here in this example? These states, 4 states, Q1, Q2, Q3, Q4. And sigma 0, 1. Delta, I'll come back to it in a while. What is the start state? Q1. What are the final states? Huh? Q4. Okay, so now delta. So let's write it as a table. So what are the rows in this table? What are the rows in the transition function table? States, right? There are 4 states. Okay. What are the columns? alphabet, symbols from the alphabet. So 0, 1, that's all. For NFA, we will also have epsilon. Okay. Now, Q1 on 0 goes to Q1. Is this right? That's all. Okay, let me show the next one, you will understand. Q1 on 1 goes to Q1 and Q2. Is this right? Yes. Just a while ago, I told you. Yeah. Each one is a set here. Whether you have two elements, whether you have one element, whatever it is, you have to put them in set notation for an NFA. For a DFA, there is no set notation. There is only one set as output, so only that set should be written. In NFA, whether you have one state or two states, whatever they are, you have to put them in set notation. Otherwise, you will be penalized. Okay. Q1 on epsilon, no transition arrow, so it is a null state, a null set. Okay. Now Q2 on 0 goes to Q3. Then Q2 on 1, null set. Q2 on epsilon, Q3. Q3 on 0, Q3 on 0, null set. Q3 on 1, Q4. Q3 on epsilon, null set. Q4 on 0, basically Q4 on 0, 1 goes to Q4. So on 0, it goes to Q4. On 1, it goes to Q4. On epsilon, null set. Okay, so this is the transition function for this particular NFA. All right. Okay. Let's move on. Yeah.
Earlier you said that if the symbol is omitted in the state, you can assume it's going to a dead state.
Yeah.
So when there's when the transition function gives 5, can we just say it goes to some mysterious dead state?
Yeah, you can think of it like that. Basically, when you try to convert this NFA to DFA, you have to introduce a dead state. But when you are dealing with NFS, you need not worry about that. So this null set implicitly indicates that it's going to dead state. Yeah. Yeah. We use no in sigma subscript epsilon here. And in the third one, Q cross sigma subscript epsilon. Yeah. No. I wrote that, no? Sigma epsilon means sigma union epsilon. Yeah. Okay. You see, every time we formally define a machine, like formal definition of DFA, now formal definition of NFA, later we will also formally define some other machines. Every time we give the formal definition of a machine, we should also give the formal definition of the computation for that machine, or formal description of computation for that machine. Does anyone remember what is the formal description of computation for a DFA? When do you say a string is said to be accepted by a DFA? We formally define that. Yeah. So how many conditions are there basically in that? How many conditions need to be satisfied? AI people, give me quick answer. What are those? Yeah. So basically three conditions. If you have a string omega which has say n characters, omega 1, 2 and so on up to omega n, then the machine will pass through rn plus 1 states. Will pass through n plus 1 states like r0, r1 and so on up to rn. These n plus 1 states need not be exclusively present separately in the machine. Machine may have 2 states, 3 states, whatever they are, but the sequence of visiting the states will be n plus 1 in total because the string length is n. So you start with state r0, which is equivalent to q0, and then you read omega 1, you go to r1, then you read omega 2, you go to r2, then you read omega 3, you go to r3, and so on. By the time you read omega n, you go to rn. Okay, so the second step is delta of ri comma omega I plus 1 is ri plus 1. You continue this sequence. Finally, by the time you are done reading all omega n symbols, you will land up in rn state. Now the only thing you need to check is whether rn belongs to the set of final states or not. If it is, then omega will be accepted by the machine. If it is not, omega will not be accepted by the machine. Satisfied. If yes, omega is accepted, otherwise it's not accepted. So this is like the formal description of the computation of the machine. We define the machine formally, that's one thing. We also need to define the computation formally. When is a string said to be accepted or not accepted? That also we are defining mathematically. We are not just informally saying, okay, maybe in this case it will be accepted, maybe this string may be accepted, may not be accepted, not like that. Specifically, mathematically, we are saying exactly when a string is said to be accepted. Okay. Similarly, we should do that for NFA also. When is a string said to be accepted by an NFA? Okay. So that's what we are going to do now. Formal definition of computation for NFA. Okay. Let n equal to q sigma not f be an NFA and omega a string over the alphabet sigma. Then we say that n accepts omega if omega equal to y1 y2 y3 and so on up to ym, where each yi is a member of sigma subscript epsilon and a sequence of states r0, r1, r2 and so on up to rm exists in Q with three conditions. Can you guess what the three conditions are? What will be the first condition? Yeah. R naught equal to Q naught. Start state should be R naught, right? The start state should be Q naught. You start with Q naught. All right. Now second one. Any guesses? Hmm? What was the second one in DFA computation? Delta of Ri comma omega I plus 1 is Ri plus 1. This is fine because you know the output is one state. But here, the output is not one state. It can be more than one state. It can be no state. It can be one state, whatever it is. So I can't just write delta of Ri comma yi plus 1 is Ri plus 1. I can't write this. Now, even if I have to write it in a state, I don't know how many other elements are there, right? So basically, it is like a process tree, right? So I may start with say R0, uh, maybe I reach some point Ri, and this from this Ri, I may have many states, possibilities. It can be X, Y, or and then Ri plus 1, and then maybe P, Q, and then this Ri plus 1 may lead to Ri plus 2. It may have some other children. Okay. Now, there may be many paths, but I am focused on one particular path which will finally lead me to some particular state Rm, which belongs to the set of finite states. Some other branch may also lead, some other branch may also end up in a accept state. But I am focused on one particular branch where I am going step by step. At any particular, whatever branch you take, you are only focusing on one child in that branch at that time, right? You're not, once you access a particular node at a level, you don't go to any other node in that level. You will go to the next node. In the next level, you may go to any node, but you will go only to one node. So at each level, you will focus on only one node, right? So this particular branch which you are taking, only this branch we are focusing on. All right. Now, in the case of DFA, it is only one branch. No, it's not even a branch. It is only one sequence. So you can just say delta of Ri comma yi plus 1 is Ri plus 1. But now delta of Ri comma yi plus 1 is actually a whole set. It is X, Y, Ri plus 1, P, Q. Just for example's sake. We don't know how many other siblings are there for Ri plus 1. So we can't write all of them beforehand. So we can't say formally, we can't represent the output of delta of Ri comma yi plus 1. We can't explicitly mention that entire set of states. But we know Ri plus 1 belongs to this level, is one of the members in this level. That much information we have. So how do I modify this condition without worrying about the siblings of Ri plus 1? I know Ri plus 1 is a child of Ri. I don't know about other children. This I want to capture as a rule. How do I do it? Okay, so I don't think I'll get an answer. I know that Ri plus 1 belongs to the output set of delta of Ri comma Yi plus 1. That's it. I just know Ri plus 1 is a member of the output set. I don't need to worry about the other members of that set. So rather than saying delta of Ri comma Yi plus 1 is the entire set whose members I don't know, I reverse it by saying Ri plus 1 is a member of the output set. That's all. And I continue like this. So through this method, I will also be accessing every element in that set. So I will also say that for I goes from 0, 1, 2 and so on up to m minus 1. So now I will access every child of Ri and I will check out every branch that my process tree can take. All right, at the end, I reach some Rn, okay, and that should belong to F. That's all. So this is the slight difference between DFA's second condition and NFA second condition. All other conditions are same. In DFA second condition, delta of Ri comma omega I plus 1 is Ri plus 1 because there is only one output state. Whereas here, it is a set of output states. I don't know the other elements of Ri plus 1, other siblings of Ri plus 1. So instead of worrying about them, I'll just say Ri plus 1 is an element of the output set of delta Ri comma Yi plus 1. Okay, so it belongs to the output set. That's what I will say. I will not list the entire output set. Okay, so let's stop here.